Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it is an honor and a privilege to be serving here today, as it is every day, here in my virtual classroom. Step one inside, I had just finished recording a 9.1 to 9.3 review that was, I guess, my own worksheet of 16 problems. And if you want to check it out, I'm sure you can find it in just historically right before this video that's being uploaded right now. That's the 9.1, 9.3 review, quiz review out of the Big Ideas Math, Integrated Math 2 textbook. This one's a little more official to that official book. Haven't done these problems yet. I believe there are, it's 17 problems on here, and I don't yet know if I'll have to use a calculator, but we'll see. So 9.1, 9.2, and 9.3, similarity in right triangles, Pythagorean theorem, special right triangles, all of that stuff. Let's go ahead and take a look at what they want us to do. All right, in numbers 1 through 3, and this is going to go relatively fast, I hope, kind of like half-hour time. In numbers 1 through 3, we'll find the value of x, tell whether the side lengths form a Pythagorean triple. I could tell you right now that these will form a Pythagorean triple if you started to become vested in the the Pythagorean triples that they are. This exists as a 3, 4, 5 special right triangle. I can tell you right now x is going to equal 15, but let's use Pythagorean theorem to go ahead and find out that x is actually 15 itself. A squared plus b squared equals c squared, x being the hypotenuse is the c squared that we'll set up. And x squared will equal 225. And the square root of 225 is 15. Now, in an algebraic problem of this sort, we would say x equals plus or minus 15. However, because distance is always positive, we're only going to have the positive version of this. I will give this the seal of approval with the Pythagorean triple. Hashtag, if you will. I'll just lay that on to say that, yes, this is a Pythagorean triple. What is a Pythagorean triple? A Pythagorean triple is a set... I don't know why I can't define this. A Pythagorean triple is a trio of integers that exist in a right triangle. As long as a squared plus b squared equals c squared, and as long as all three values are integers, you have a Pythagorean triple. There are some classic ones, such as this one being a 3, 4, 5 Pythagorean triple. 9 is 3 times bigger than 3, 12 is 3 times bigger than 4, and 15 is 3 times bigger than 5. So, as far as triangle similarity goes, it works. Number 2, I can say off the bat, will not be a Pythagorean triple. There isn't a 7, 8 blank Pythagorean triple, so I don't know what the answer is, but we'll find out shortly. 7 squared plus 8 squared equals x squared. That's 49 plus 64, which is 113. Not 113x. Ignore what I just wrote. X squared equals 113. And I take the square root of both sides. 113, I don't know if that divides with anything. Like if it has any, not only, it might be a prime number. For now, I'm going to say that it is, unless it randomly divides with like 13, which it doesn't. Even if it did, I don't think it's any perfect square values. The whole goal is to ask if it can simplify in some sort of way. I don't believe it can. Is this a Pythagorean triple? No. So I'll just leave off the Pythagorean triple seal of approval. Let's do this. Let's circle this one like that. And then here we'll put it in red and cross it out. Not a Pythagorean triple. It's been denied. Number 3. X, not a Pythagorean triple, by the way. X is one of the legs. Normally I don't redraw these. I don't know why I'm doing this here. X is one of the legs of this right triangle this time. So I won't do 8 squared plus 4 squared equals x squared. No, X is one of the legs. So it belongs with the 4, also one of the legs here, and we try and find x within this guy. So we subtract 16 from both sides instead of combining those through addition, and we get 48, and we'll take the square root of both sides here. 48 is not a perfect square. 49 is, so it would have been really close to 7. But we're going to simplify this radical as we would, finding the largest perfect square factor that can come out of this, which is 16. The square root of 16 times the square root of 3 is the same as square root of 48. The square root of 16 is 4. So we'll get 4 root 3. Pythagorean triple? Nope. Simplified radicals. You don't treat this 3 as an integer. No. It's the square root of 3, not an integer there. There's numbers 1 through 3. All right, numbers 4, 5, and 6. Verify that they form a triangle. Is the triangle acute, right, or obtuse? So the first thing, when they say to verify, I guess that means it will be. That was the case in the problem set when we actually did section 9.1. So to verify it, we just got to make sure that the two values, when they add up, that when the two smaller values add up, that it is indeed greater than the third side itself. That's the triangle inequality theorem. 56 is indeed greater than 40. So we verified it's a triangle. Now, is it a right triangle, or is it acute, or is it obtuse? That's the question at play. So let's go ahead and take a look. 24 squared plus 32 squared, how does that compare to 40 squared? I know 24 squared. I don't know 32 squared. Use a calculator. I probably need this anyway because I don't know. 2024. I should have known that actually. And that's 1600. That's 1600. 1600 equals 1600. So the whole comparison here is, it's kind of the converse of the Pythagorean theorem. If a squared plus b squared equals c squared, then you have a right triangle. A squared plus b squared here does equal c squared. This is a right triangle. So when they're saying identify, whether it's or determine, what do they say? Oh, is it one, the other, the other? It's a right triangle. Now we'll talk about acute versus obtuse, as I'm sure we're going to run into the next couple problems. Let me address my sniffles here first. Been having a lot of allergies lately. You've probably heard it in my recent videos. Hold on. Yeah, I'm sure you don't want to hear a bunch of that. Okay, let's keep moving forward. All right, number 5. 7, 9, and 13. Is 7 plus 9 more than 13? Yeah. But let's officially verify that. You know, it's one of those things, it kind of sounds, like, is 7 plus 9 more than 13? You say, yeah. I'm like, prove it. Because 7 plus 9 is 16. And 16 is more than 13, right? Get into the nitty gritty. At least show me that. If they ask us to, let's do it. 16 is more than 13. Great. Let's go ahead and work toward that Pythagorean theorem setup. How does 7 squared plus 9 squared compare to 13 squared? And of course, I'm putting 13 on this side because it's the longest of the three sides. If it is a hypotenuse, it would be the longest. So 49 plus 81. And this is 169. So is 49 plus 81 more than 169? I actually thought it was going to be. I don't know why I thought it was going to be. This is clearly going to be acute. No, it's not. So this is 130. 130 is less than 169. So what does that mean? When a squared plus b squared is less than c squared, you're dealing with an obtuse triangle. That's what this is. The why of the matter is just that A and B are small and C is largely overpowering comparison. It takes that right triangle thing and C is now going, I'm bigger. And therefore you have to spread out for me to be who I am. So that's just my best way of saying it. There's not like a proof version of that, but that's what I'm going to say. All right, number 6, 12, 15, and 10 root 3. Now, if it's just a pattern that they just go in ascending order like they did last time, then 10 root 3 would be the biggest number. I happen to know it actually is the biggest number because I know that root 3 is around 1.7. But if you didn't know, and 10 times 1.7 is around 17. But if you didn't know that, find means by figuring out what it is. Use a calculator and do 10 root 3 to figure out what it is. Or just square the value compared to 15 squared. Right? 10 root 3 squared, I think I have to sneeze, is 300. You have to sneeze. Give me a second. I'm going to pause this. Probably going to sound a little stuffy. Sorry. But anyway, 10 root 3 squared is 300. 15 squared is 225. So, all right, this one's the bigger number. And 12 squared, just to, we're going to do these anyway, is 144. So let's do our a squared plus b squared equals c squared right now. 12 squared plus 15 squared equals, not equals, does it equal, how does it compare to 10 root 3 squared being the biggest number? Of course, we're trying to add to see if it becomes that. This looks like it'll be bigger, but let's show what it actually is. It is 369. And that is indeed bigger than 300. So now A and B this time, here's A and B, the right angles of a triangle, and it says, I'm bigger. You have to shrink, making it more acute. This will be an acute triangle that we're dealing with. Right there. Whoops. Sorry if you didn't see that. This will be an acute triangle when it's greater. Sorry. Let's deal with this. All right. That was 4 through 6. Let's go to 7 through 9, this is now section 9.2 on special right triangles, the 45, 45, 90, and the 30, 60, 90. Number 7, let's just draw it. Number 7, we have a right triangle with length 6 and an unknown x, an unknown y, and a known 45 degrees. This is indeed a 45, 45, 90 triangle, which has a special ratio relationship in how the side lengths compare. In a 45, 45, 90 triangle, you may understand that's an isosceles triangle. If this is 6, this is actually going to be 6 as well. X is 6. Now, it runs deeper than that. This is a 1-to-1 to root 2 ratio relationship where the 1-to-1 is in 6 and x. These are 1-to-1. They are the same. Root 2 is how many times larger the hypotenuse is compared to these guys. If you didn't know that, you could, of course, always use Pythagorean theorem. You now know that this is 6. 6 squared plus 6 squared is y squared. You could solve that. But it's going to be root 2 times larger. Y is going to be 6 times the square root of 2. And that is literally the answer to both of those. And that is simplest form as well. So that's number 7 in a nutshell, is a 45, 45, 90 triangle. And the only one that looks like we're going to be running into. Unless there are more on the bottom. I can't tell. Number 8. Number 8 has an 8 in it. Let's draw that. Okay, we got a right angle here. This length is 8. Unknown x, unknown y, and 30 degrees there. This is the 30, 60, 90 triangle. 30, 60, 90 triangle has a 1 to 2 to root 3 relationship. And that's the way I say that. 1 being the shortest side, opposite the 30-degree angle, which is the smallest angle. 8 is the 1 in this case. This is all similarity based. X represents the 2, the hypotenuse. It's twice as large as this 8 here. X, you are going to take that 8 and multiply by 2. And you get 16. Hypotenuse is twice as large as the short leg in a 30, 60, 90 triangle. And root 3 references the y. You don't go from x to y like this. You go from the short leg, once again, because it's 1 to root 3. As in, if this were 1, this is root 3 times larger. We multiply this by root 3 to figure that out. Y is going to be 8 times the square root of 3, literally just 8 root 3. And that is its length. That is your 30, 60, 90 triangle there. But we have one more, it looks like, and we can deal with it. Let's see how we do. Number 9. Number 9, I have yet again another 30, 60, 90 triangle, but this time we have the hypotenuse as 10 root 2, finding this x and y. The 60 is here, which means the 30 is there. So 10 root 2 being the hypotenuse, that's twice as long, in the 1 to 2 to root 3, it's twice as long as the short leg. So we will divide this thing, not by root 2, but just by 2. So x is 10 root 2 divided by 2. Right? You're dividing that by 2, taking half of it. You get 5 root 2. That is x's length. And I want to use 5 root 2 to get the y value here. This is the 1 to root 3 relationship portion of this. Let's multiply the short leg by root 3 to figure out y. Y is 5 root 2 times root 3, and root 2 times root 3 is root 6, which cannot simplify at all. So there it is, 5 root 6. All done. All right, numbers 10, 11, and 12. And these actually were not on my worksheet review, although I did talk about geometric mean for a completely different reason. Find the geometric mean of the two numbers. Now, I'm going to set it up in the proportion basis of this. 6 and 12. Finding the geometric mean. I'll set up the proportion that... the whole concept is that in a geometric sequence, x is some number between 6 and 12, meaning you have to multiply, you have to multiply 6 by something to get x and x by something to get 12. It's not 9, it's not the halfway number in between or anything like that. But whatever that something is the same. So whatever x divided by 6 is, 12 divided by x is also the same thing. Here's an example of a proportion you're allowed to set up doing this. You can do it like that. You can do 6 over x is x over 12. That's the classic way people would write it, even though it's not the common ratio. Either this or that kind of thing is going to be fine. Ultimately, you cross multiply. You get x squared equals 6 times 12. And I will go ahead and actually multiply those out. But this is also the formula that they're going to have you write. The geometric mean of 6 and 12 is set up as such that x squared equals 6 times 12, or the square root of 6 times 12, which is what I'm going to do next. But I'm going to deal with it in terms of proportions. I want you to know where it's coming from. I want to talk about proportions in general. So square root of 72. So 72, 36 can factor out of 72. So square root of 36 is 6. You get 6, whoops, not root 6. 6 root 2 as the answer there. You can only get positive integers here. It's what they want. So x is 6 root 2. They didn't say only positive integers, but I think in the section they did mention that. All right, number 11. Let's find the geometric mean of 15 and 20. So number 11, 15 and 20. This is, once again, you could set something up like 15 over x equals x over 20. It's the number in between that you got to multiply by from those. So cross multiply, we get x squared equals 15 times 20. 15 times 20 is 300. I think that number, it's large, but I think it's clean enough that I know what I want to do with it. So square root of 300 in that case. 100 can factor out of here. Square root of 100 is 10, and I get 10 root 3 as that guy. And we already talked about 10 root 3 being around 1.7, 10 root 3 being around 17 something, so I guess that makes sense that would be the answer. And then number 12, we have 18 and 26. If you'd like to go in the form that doesn't use the proportion at all and go straight into the answer, it's x squared equals 18 times 26, right? That's the idea. See where it came from, though. If you don't remember that, see where it came from. Now we take the square root here. I don't know 18 times 26, and it's probably a stranger number that I don't know what I want to do with it. So here's what I'm going to do. Leave it as 18 times 26, take its square root, but we're going to simplify as much as we can out of these. So what do I want to say about that? Square root of 18. Root 9 times root 2 gives me 3 root 2. 26 doesn't have a perfect square factor. But I do want to break it up into root 2 times root 13. And the only reason I'm doing that is because I want to pair it up with this root 2. Instead of simplifying something later, let's just do it now. Those can simplify. Root 2 times root 2 is 2. And I get 3 times 2 times the square root of 13, or 6 root 13. And that, my viewers, is the answer to number 12. Okay. Numbers 13 through 15. Identify the similar right triangles, then find the value of the variable. So, by identifying them, there are so many ways we can talk about it. Should we do a redraw of these triangles, or should we just name them by what we do? The first problem, I'm going to do a redraw. The next two, I don't think I will. But what I mean by a redraw is get all three triangles redrawn so they all face the same direction. Then you can identify the similarity exactly for what you want. See, there's this big right triangle ABC, right? B, right here, right? B is the right angle. B is the right angle. Go into that short leg of the big triangle is C, and then A is across the hypotenuse, the other side of the long leg. Let's draw the other two triangles the exact same way. This medium-sized triangle right here, let's draw that exact same way, but look at its letters. D is the right angle here. The short leg to here is B, and the long leg to there is A. And then in the small triangle, we have also right angle of D right there. The short leg is C, and to the long leg is B, like that. In this redraw, this allows me to make a similarity statement. It says identify the similar right triangle. So let's go and do that. That's triangle. If I call this one ABC, the first guy, boom, 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 it's similar to ADB. Now that they're all drawn the same way, we know exactly what's supposed to correspond, and BDC. So that is the identify the similar triangles portion, and the redraw can help you with that. You don't have to use that based on understanding how I did this redraw, but those three are similar. It says find the value of the variable. The redraw can help me with that as well. In this redraw, B to A is unknown, B to C is unknown, but A to C is known. If you add 8 and 4, you get 12. That's the hypotenuse of the big triangle. From B to D is X. You see that here and you see that here. It's the short leg of the medium triangle and the long leg of the small triangle. Remember these phrasings that I'm making for the next question that we do, because I'm not going to redraw that one. The long leg of the medium triangle is 8. I don't know its hypotenuse. The short leg of the small triangle is 4. I don't know its hypotenuse here. The only parts that have corresponding aspects for which I can set up a proportion include the short legs of the medium and small triangles and the long legs of the medium and small triangles. So I can do something like x over 4 equals 8 over x. That's the idea anyway. There's more than one way to solve this. From this triangle alone, we could do it, but I want to take advantage of the redraws that I have, set up that proportion, and solve. X squared is 8 times 4, that's 32. Take the square root of both sides, you'll get root 16 times root 2, which is 4 root 2. That's the value of x. Now, in numbers 14 and 15, yes, at some point I have to mention geometric mean. X is the geometric mean of the numbers 4 and 8. That's something where you'd have to know the altitude is the geometric mean of these two, that kind of stuff. I'm not too big on that. I've mentioned that time and again. I mentioned it in my review worksheet. I mentioned it in section 9.3 because you don't necessarily learn anything about it unless you dig into the proofs, in which case build the proportions yourself. Number 14, I'm going to copy that diagram again, and let's do it without the redraws. Let's try and identify the similar triangles by talking about long legs, short legs, hypotenuses, things like that. Let's start with the first triangle, the big one, triangle EFG. I like to say the first one alphabetical if I can. That does not mean the others will be alphabetical at all, not even close. But that's the big triangle. Which one's the medium triangle? Is it this one or this one? Well, it's this one. From 6 to 9, 9 is bigger. That doesn't necessarily mean anything, except by this guy being the geometric mean of these two numbers, this is the number in between. Therefore, this is the short leg of the small, the long leg of the small, the short leg of the medium, and the long leg of the medium. This is the medium triangle. So, in the medium triangle, this F, H, and G, let's look at how I went from E to F to G. From E to F to G, E, F, G, I went across the short leg and then the long leg. So let's go across the short and long leg of the medium triangle right here and right here. F to H to G. F, H, G across short and long. Now let's go across the short and long of the small triangle. Short goes from E to H. Long goes from H to F. E, H, F. So yes, you can absolutely come up with these without a redraw, but you also still have to solve the variable without a redraw as well. Y. I have to solve for Y. Now, Y represents two different things in two different triangles. Y can represent, for example, the long leg of the big triangle. Now, I want to divide Y by something that would correspond, either something else in the big triangle or a long leg in another triangle. The long leg in the medium triangle is 9. So the long leg in the big triangle is Y, the long leg in the medium triangle is 9. Let's set that equal to something else in the big triangle and something else in the medium triangle that we have. The only other thing we have in the medium triangle is Y, the hypotenuse. That's the medium triangle. Do we have the hypotenuse in the big? If you add 6 and 9, yeah, you get 15. So that can be a proportion setup. Now, when I cross multiply these things, I get Y squared equals 9 times 15. Maybe one of those ones that I won't actually simplify, but also a good time to let me state what else you could have done with this problem without going to the proportion. If you know that Y is the geometric mean of the numbers 9 and 9 plus 6, 15, then you could set it up exactly like that. Y squared equals 9 times 15. I hate to poo-poo on that stuff, but I do. If you know that, great. You're probably saying, Mr. Robinson, why don't you just say that? I'm not going to just say that. I'm going to set up proportions. But yes, that's our setup, and we can take the square root of both sides to solve. So the square root of 9 is 3. The square root of 15 actually does not have anything to simplify to. No perfect square factors. We're just going to leave it like that. We get 3 root 15 for Y. Number 15. If we did do the geometric sequence thing that you just saw in the, not geometric sequence, geometric mean thing you just saw in the previous problem, this one applies in a similar fashion. If I were to do a very fast setup, it's not about Z, it's about 18. This guy, 18 squared equals this guy times this guy, 12 times Z. That would be my setup, and I'm all good. I think I've seen this problem before. I think we did this one. It wasn't probably the same problem, but I think I've seen this multiplication. Yeah, you'd be good. If I wanted to talk more proportions, I would do what I said before. Let's represent Z if we needed to. Z is the hypotenuse of the big triangle. Do I have a hypotenuse in another triangle? Yeah, the small one. Small one right here. So Z over 18. Hypotenuse big, hypotenuse small. Let's do something else in the big and the small that correspond. I have the short leg in the big. Do I have the short leg in the small? Yeah, 12. That'll work out. When you cross multiply, what do you get? 18 squared is 12Z. So I'll divide both sides by 12. I was going to say z. And I get z equals, and I think this is how I remember this problem, because without a calculator, I don't really know. I know it's 324, but I divided like this, and I need to do it again because I don't really remember. 18 twelves is 3 halves. 18 divided by 2 is 9, and 9 times 3 is 27. Z is 27. No calculator needed. Calculator, not calcu now. Okay. 2 more questions. Television sizes are measured by the length of their diagonal. True. You want to purchase a television that is at least 40 inches. Should you purchase the television shown? Explain your reasoning. So this is a question on Pythagorean theorem. If I have this television here with a width of 36 and a height of 20.25, we want to figure out what that diagonal is. The television is rectangular. It has a right angle there, so it's a right triangle. Let's try and figure out what that x is. If x is more than 40, yeah, we'll do it. If it's less than 40, no. If it's equal to 40, yes, that's allowed as well. So we'll do a squared plus b squared compared to c squared. You know what? You know what I should do? Instead of putting x, let's put 40. Let's put 40, and let's see if this is greater than or equal to our 40 squared. Right? That's what we want to check on. Is this the case? Is this the case? 36 squared. 36 squared. 1296. 20.25 squared. Weird number. 410.0625. And 40 squared is 1600. I think it's going to beat it. So that plus 1296. Let's get official numbers. We get 1 second, because here's the thing, right? I don't need to solve what the value is exactly. I just need to make sure that this was more. Is it? It is indeed greater than 1600. That checks out. So, should you purchase the television shown? Well, is it a? What brand is it? You should purchase the television shown. Or I should, whatever. You should purchase the television shown because it is more than 40 inches in length. I'll say at least 40 inches length. Did I find out how many inches it was? No, I'd have to take the square root of that number right there. I don't know. I just know it's more than 40. And that's the idea. Okay. One more question, number 17. Let's take out the sniffles first. Okay, so number 17. Each triangle shown below is a right triangle. This is all of 9-1 to 9-3, it looks like they're saying do. Oh, I didn't see that this said 9-1. So yeah, totally Pythagorean theorem-esque. Each triangle shown below is a right triangle. Okay. A. Are any of the triangles special triangles? Explain your reasoning. Interesting. Okay, so what you want to do is understand that 1 to 2 to root 3 relationship and ask yourself if that thing is what it is. If we scan through these, we're going to look at... I'm going to bring them on my side here. So over here, when we look at these, A is a special right triangle because it is an isosceles right triangle, much like the 45, 45, 90. So yes, A is one of them. It says explain, and I just did my explanation there. B has a 1 and root 3 relationship here. This is 3 and 3 root 3, but that's a similarity aspect we're talking about. 1 to root 3. This is, in a right triangle, this would automatically be 2. You might say, how do you know that? Pythagorean theorem. There's only one way that 1 and root 3 would work out to make 2. So yes, B is 1. This is the 30, 60, 90 triangle that has a racial relationship. This is 6. This is 6 root 2. That's a 1 to root 2 relationship. In the same way, this, by Pythagorean theorem, this would be 1. So this is a 45, 45, 90. So C is indeed 1 as well. D is a Pythagorean triple. It's a 3, 4, 5 triangle, but it's not a special right triangle. It's special in its own right, but not special in the 45, 45, 90, 30, 60, 90 way. This is called a Pythagorean triple, not D. And E, this is 1 to 2 relationship here in a right triangle, so this must be a root 3 by comparison. This is a 30, 60, 90 in that way, so E also is These are the special right triangles. D is special in its own right, being a Pythagorean triple, but not in the 45, 45, 90, 30, 60, 90 way. List all similar triangles, if any. Oh, yeah, so any 45, 45, 90s would be the same. So I'll call it triangle A is similar to triangle C, and triangle B is similar to triangle E. Those are both 30, 60, 90s. D is its own thing. Part C, find the lengths of the altitudes of triangles B and C. Okay, let me copy those one more time. This is kind of a 9-3 question. You're going to have something else floating there in the ether. I'll kind of hide it. Give me 1 second. Okay, find the altitude of triangle B, this guy right here, to the hypotenuse. Find the altitude of triangle C, this guy right here. Okay, now I kind of want to do C first because of its nature. Like I said, this could be a 9-3 question, but it also doesn't have to be anymore. 6 root 2, this is a 45, 45, 90 triangle. It's an isosceles triangle, which means this altitude bisects this thing. This is 3 root 2 right there. This length right there is 3 root 2. So, and this is, by the way, once again, another 45, 45, 90 triangle. Because the bisecting. If it's 45, 45, 90, that also makes this thing 3 root 2. This is a 1-to-1 to root 2 relationship. So the altitude of C, is 3 root 2. I don't know how else to put that better, but I'm just going to put alt C. B's altitude, I kind of feel like I need to get, this is easy because it's 1 to 2 to root 3. So this whole thing here is 6, right? That whole thing is 6. And I feel like I kind of need to use that. Let's move these down a little bit. In terms of how to use X with this. Because X represents the short leg of... X is the short leg of the medium triangle. And 3 root 3 is let me say that again. X is the short leg of the medium triangle, and 3 is the short leg of the big triangle. So for this guy, I can say X over 3. And I can do medium and big triangle again. The medium triangle's hypotenuse is 3 root 3, and the big triangle's hypotenuse is 6. That's what I can use for that one. This 3 isn't really used because I don't know the short leg of the small triangle, with that being the short leg of the big triangle, and X only represents the long leg of the small triangle, and yet you might be able to use 3 actually. I would have to think that through. Let me consider that. The long leg of the small triangle hypotenuse, yes, I could say the long leg of the small triangle over the long leg of the big triangle equals the hypotenuse of the small triangle over the hypotenuse of the big triangle. So I can use this as well. You might say, well, which one should I use? It doesn't matter. When you cross multiply, look what happens. 6 multiplies with X and 3 root 3 multiplies with 3. So either or is fine there. So when I set that up, I'll get 6X equals 9 root 3. And then you divide both sides by 6 and you get X is 9 root 3 over 6. And that reduces to 3 root 3 over 2. 3 root 3 over 2. Now, you might be wondering, Mr. Robinson, what about that geometric mean thing that we would do sometimes? That actually can't apply here. You actually can't use it here. This is one where setting up proportions is a better likely outcome for it. And that's kind of why I wanted to save this problem last. So I said X. Let's say the altitude of B. Altitude of B. All right, so that should be the answer to that one, and that'll be it. All right, guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. I know I ran just past a half hour, but hopefully it was sufficient enough for your needs. Next section would be 9.4 and then 9.5 and 9.6. I don't know when those videos will be up, but those are all trigonometry based. And I have a lot of other videos on trigonometry here and there, and I'm sure I can post those videos if you need some time within. Just search Mr. Robinson trigonometry stuff. You'll probably find it. Thanks so much for watching. Take care, and I will see you in the next one.